I'm going to show you a video on how to work through these chemical combustion problems. And so if I can have you take notes while I'm walking you through this. This will be the first page of your handout. So I will always offer you a data table with information which you can apply to the actual calculations. So the easiest thing for me to do is always to draw a sketch of the lab setup. I have here a container of water. I have 125 grams of water, and it's being heated by methane. I'm told that I have 0.38 grams of methane that I burned. And when I burn that much methane, it heats the water from its initial 19.5 degrees Celsius to 59.9 degrees Celsius. That's all information that I've gotten over here, okay? One of the things that it's also asking me is to convert my grams into moles of fuel burned, and so this is a simple dimensional analysis problem. I look at the periodic table, see that CH4 is 16 grams, and determine that I burned 0.04 moles of CH4. Next, what I want to do is work through the balanced chemical equation. And from last class, you remember that CH4, when it combusts, any sort of fuel will always require oxygen, as well as producing carbon dioxide and water. So with that said, I want to do the structural formula. The structural formula is I have CH4 in a tetrahedral shape, then 2 oxygens in linear, carbon dioxide in linear, and then I have 2 bent oxygens. Potential energy graph, we'll work on that next class period, and so you can ignore those for right now. So the first question is asking, calculate how much energy is absorbed by the water or given off by methane. With that said, thank you. So having said that, we know that we cannot put a thermometer into the methane because it'll burst, but we can assume that all of that energy that left from the methane went into the water. So if we can find how much energy went into the water, we can also determine how much energy came out with methane. And using the Q equals MC delta T, I was able to determine that it was 21.1 kilojoules of energy that was absorbed by the water through the methane. So 21.1 kilojoules left the methane and got transferred into the water. So that tells me that I know that 0.38 grams of methane releases 21.1 kilojoules of energy. I can use dimensional analysis. So if I know that 0.38 grams release 21.1 kilojoules, I can make that into a conversion factor and can determine then what 1 gram is going to be. So 1 gram of CH4 is multiplied then by that conversion factor so that they cancel out, and my answer is 55 kilojoules per gram. So now I want to know the molar heat of combustion. Remember, heat of combustion is how much energy 1 gram releases. Molar heat of combustion is how much energy does 1 mole release. So I'm given how many moles I have over here. I can do a straightforward mole to gram conversion and use this value here to determine how many kilojoules of energy are released, and it is then this here. Okay. Perhaps a more simplified version of how to work through molar heat of combustion. Again, molar heat of combustion is the amount of energy released by 1 mole, is that at this point we know that you have 0.024 moles of CH4, and they release 21.1 kilojoules of energy. So in that case, what you can do is you can simply create this into a conversion factor. Remember, when things are equal to each other, you can do that. And I want to know what 1 mole releases. So 1 mole of CH4 And then we use this conversion factor. So we know that 0.024 moles of CH4 releases 21.1 kilojoules of energy, and you'll see a number that is close to 880 kilojoules. Remember to check your significant figures to make sure that you have those. There's other ways of doing this. As long as you get to the same answer, that's all that matters. So once we've figured out what our molar heat of combustion is and our heat of combustion, we can apply that to a new scenario. So let's say in my new scenario, how much energy would be released if I have 5.3 grams of methane? Well, I know that 1 gram of methane releases 55 kilojoules. So using dimensional analysis, I can make that into a conversion factor and get these answers. That holds true for moles as well. Instead of having just 1 mole of methane that I burned, I had 15 moles of methane. I simply take the conversion factor for the molar heat of combustion, which was 880 kilojoules per mole, and do my conversion. And I can recognize that this is actually a mistake. If you can please make sure that that actually is 880 kilojoules right here, not 55. Okay, so change that to 880. And that should get you the answer of 13,000. The last piece is a good old stoichiometry problem. Based on the chemical equation, if I know that I have 0.38 grams of CH4, how many grams of oxygen am I going to need? So I do a gram to mole conversion, mole to mole, using the periodic table, and lastly then a mole to gram conversion. So the last step in all of this, just closing it down, is actually adding the value of energy to the chemical equation. So for this chemical equation, we assume the number 1 here that tells us if we have 1 mole of CH4 burned, we now are going to add, and I haven't done it here, but please do it on the paper, plus 880 kilojoules. Okay, so this should say now plus 880 kilojoules. In the past, we've always said just write the word energy, but we now know that 1 mole releases 880 kilojoules. If I had a 2 in front of here, I needed to take that 2 and multiply it by my molar heat of combustion to put that in the equation. And what you will notice is that for some of these equations, and later on, for example, in experiment the last experiment where it says fuel efficiency of diesel on the last page, you notice that 4 moles of C12H23 releases 10,124 kilojoules. So that is what 4 moles release. Good luck.